Hi, everyone. Thank you for coming to my presentation. I truly apologize that I couldn't make it in person this year to WITS. And I also couldn't present on Zoom. It's a little too early for me. It's 4:30 a.m. So I hope you're going to enjoy the recording of my presentation. And without further ado, I'm going to present my work on human-machine attention mechanism, and in short, HMAM. This work is led by my PhD student, Avichai Shriki, myself, Inbal, and my colleagues, Ahmed Abbasi and Dovte. So let me start by defining attention for the purpose of this work. So here's a Yelp review on a restaurant. What we are going to do is we want to classify this review as either a positive or a negative sentiment. Attention is the emphasis that we put on words in this text in order to be able to classify it correctly to positive/negative sentiment. Here's an example. So if we read this text, the words like enjoy, tasty, love are words that can help us understand that this at large is a positive sentiment expressed by the reviewer. In fact, research shows that humans use two types of attention processes. The first process, or the first system, is the intuitive system, which is unconscious. This is the system that we usually use 95% of the time to do daily tasks, to read text, to analyze visual images or videos, and so on. The second system, which I'm actually more interested in this project, is the rational thinking mechanism or process, which is the attention that we put on purpose, intentionally, to pieces of information, text or words in my context, in order to better understand the text and be able to make decisions on the task, like classifying the text as either positive or negative. Machines also use attention mechanisms. In 2017, a famous paper called Attention is All You Need by Vaswani et al. Was published and opened the door to contextual understanding of text. How do they do it? They added attention mechanism. Attention in this context is a vector or matrix that is a vector or matrix of terms importance that defines which terms are more or less important to understand the text. I want to explain this image for a second because I'm going to use it later on. So what you see here is two sentences and the birth attention specific layer. This is layer 7, but it's not important. And you can see that what happens here is first that BERT tokenizes the sentences and add two special characters. The CLS tag, which is the representation of a sentence to an extent, and the separator tag, which is the end of each sentence in the block or in the sequence. The attention is a matrix of term to term. For each term, we put attention on different terms. I'm not going to explain all of it, but in general, we're going to put attention on different terms in order to understand it. For example, in order to better understand the word on in the context of the first sentence, we need to understand the word set. So this is basically the idea. When we compare the two attentions, we can see that they're quite similar. For people or for human, this is the top part of the image, people put binary attention on terms. Do I focus or not focus on this term? Machines, on the other hand, put continuous attention to terms because it's a weight, it's a scoring system. How much weight I give to this word. But if you compare the correlation between the human attention and the machine attention, which is a work performed by Senetel in 2020, you can find that the correlation is quite high, is between 0.63 and 0.79 in their experiments. What we are going to claim in this paper is that if we combine the two attention mechanisms, the machine attention and the human attention, we can actually get a better machine attention mechanism that perform the tasks better, the prediction tasks better. Looking at the literature, we could find two works that are quite similar in their ideas. I'd like to introduce them as a baseline to what we did. The first is a paper from 2018 by Zhu et al. They tried to use lexicons to supervise an attention mechanism. Basically, they enforced the system to put attention to terms in a sentiment lexicon. They use it for sentiment task, obviously, and they could improve what was state-of-the-art classifiers at the time, like RNN and BLST. BERT was not available then. The second paper from 2021 by McGuire and Tomura tried to use EEG and eye tracking signals, again, to supervise the attention mechanism of a BERT-like system. They couldn't actually improve the performance of the baseline model. And the reason they couldn't improve it is twofold. First, both EEG and eye tracking are highly variable. So there's a lot of noise in these signals. And it's very hard to differentiate the signal from the noise in order to use the information about what people put focus on or people put attention on. The other explanation or possible explanation why this didn't work is that they use the unconscious system of human, implying that they asked people to generally read text, not intentionally for classification tasks, read the text, and then they measured what people put attention on. What we're going to use is we're going to use the conscious system with a low variable alternative, like the one used in Sandpaper for the Yelp dataset. Here's what we do. So here's an illustration of BERT architecture. I'm sure you're familiar with it, but I'm going to go through that in any case. So I have sentences all tokenized into words, for example, going through 12 transformer blocks. Transformer blocks go from 0 to 11. Okay, the first one is number 0, the 12th one is number 11. And each block has two layers, the self-attention layer and the embedding layer. At the end of this architecture, we have a classification head specifically for the sentiment task that we're interested in at this point. And then we're predicting the sentiment class of each sentence. In our work, we're going to interfere with this mechanism by adding the human attention into the transformer blocks. We're considering three alternatives. The first alternative is using attention as a prime and enforce the first transformer block to initialize the attention layer with the attention of a human. The second alternative is to use attention as a normalizer. In this scenario, we're going to fine-tune BERT for the classification task, regardless of the human attention, and then we're going to normalize the last attention layer with the human attention layer, basically combining the two and replacing the less attention before the prediction task. The second alternative is attention as loss, which means that we supervise not only the prediction or the classification, but we also supervise the attention mechanism, the different layers, by the human attention. Not surprisingly, the last alternative performed best from all of our experiments. So I'm going to present the last alternative, and you can find the other alternative in the paper if you like. In this scenario, the loss is defined by two parts. The first is the regular classification loss, the softmax head. The second one is the attention loss, which is defined as the cosine similarity between the human attention and the machine attention in the last transformer block, the 11th block, which is the 12th, the 12th block in the illustration that I showed. We ran the experiment on the Yelp data by SEN. The Yelp data by SEN is a tagged data in each 2,000 reviews that are balanced on their sentiment, meaning half of them are positive, half of them are negative, were tagged or labeled by 3 persons each. Each person was asked to tell us or tell the system which words he puts attention on. In general, the sentiment task here is extremely easy. Even without taking human attention into account, if we use BERT to predict just the label, just the sentiment class of all the instances, we get a very accurate system of AUC of 0.98, which is extremely high. What we're going to do is we're going to make this problem a little harder. We're going to undersample the data on various sizes, meaning we're going to have less observations running from 2050 to the entire data, which is 2000. And we're also going to make the data imbalanced, meaning that we're going to take one of the classes, negative, for example, and we're going to downsample it such that it accounts for only 1% of the data, 2%, 5, 10, and so on. So our data is going to be extremely unbalanced. For human attention, we're going to get the average of the active words or the highlighted words as they defined in the experiment. For machine attention, we're going to take the last layer, like I told you, the last transformer layer, and we're going to take the average of the different heads. Attention has 12 heads. I didn't go through the details. We're going to average through them, and we're going to consider the attention between each token to the CLS tag, which is the special tag that represents the sentence. So here's our performance. This graph illustrates the performance on a small data size of 250 instances. The x-axis is the imbalance ratio between the positive and the negative class. The y-axis is the mean AUC across our experiments. Blue for BERT, yellow for HMA model with the third alternative. You can see that when the imbalance is extremely high, our model performs much better than BERT. So adding human attention is significantly improving the system. It's very important. When the data is balanced, on the other hand, the improvement is very low. The same holds for different data sizes. As you can see, when the problem is hard, very small ratio, imbalance ratio, very small data sets, human attention is important. When the problem is easy, we have enough examples from each class. There is no improvement or no significant improvement when we use HMAM compared to BERT. Next, we computed the labeling cost reduction. Labeling cost reduction is the difference in the number of instances that one needs to label in order to reach the same performance between HMAM and BERT. What you can see here is that when the imbalance ratio is 0.01, we could actually save on average 780 or over 780 instances that need to be tagged in order to reach the same performance. That's huge. When the imbalance ratio was 5%, we could save approximately 484 instances on average when we use HMAM compared to BERT. Next, we wanted to understand why. Why HMAM works better than birth. What we did to understand, to explain the differences between the mechanisms, is performing an analysis showing which terms HPAM puts more attention on and birth puts less attention on, or vice versa. And we found interesting results. For parts of speech, for example, we found that H1 puts much more attention on adjectives than birth. That makes sense because that's what we people do. We put attention on adjectives. We also find a replication of the negativity bias of people. People put more emphasis on negative terms versus positive terms, and we see the same for HMO. We found additional results. For example, people put focus on spelling errors, while birth doesn't. HMAM obviously does the same as people. And there are some special entities that HMAM puts more attention to compared to birth. We're still working on it, so hopefully I'll have more results next time I'm presenting. The last thing I'm going to present to you is the variety analysis, meaning on how many terms human puts attention in a sentence compared to birth. What we find here is the standard deviation of attention by human is much higher than that of birth and much higher than that of HMAM. That means that on average, human puts more attention to more words. Or in other words, birth doesn't need a lot of words to understand the text. That can be good and bad depending on where the information is found and how confusing or complex the sentence is. Interestingly, when we put these two together, we find that HMAM actually puts the lowest standard deviation, so the attention on fewer words, but obviously the words that are more significant according to both systems, the human and the machine. To conclude, human attention can help machine to better understand text. We can improve both performance and reduce the label cost. What we are doing now is working on few different things. First, on explaining why the mechanisms are different and what exactly differentiates the mechanisms, maybe in order to be able to replace the attention mechanisms of machines without needing the input from human. We're also working on another data set that we're currently collecting and a little bit harder from the sentiment task, which is predicting personality traits. And we're also working on alternating the attention mechanisms of other large language models, such as BERT. And I can already assure, because we tried BERT already, that it works for that too. Thank you again for listening to my presentation. If you have any questions, you can contact either me or my PhD student, Avichai, which will probably have better answers, so maybe you should contact him only. And again, thank you, and hope to see you in the next conference. Bye for now.